Let's get going. Remember that we introduced a few assumptions in modeling flight vehicle structures, including those made out of composites. So we had introduced 3 of those assumptions. So we will start with the 4th one today. So if you recollect the assumptions that we had, the first one was that it's an elastic material, that the material is linear, and then that it had no body moment. So let's rewrite the mathematical conclusions that we got out of that. The first one saying it's elastic, essentially said that it's a unique valued function between the stress and the strain. So we can write sigma ij as sigma ij of gamma KL, or the other way around, that gamma KL is some nonlinear function of sigma ij. But the important point is that both of these are single valued. Okay. So that's as far as elastic is concerned. And then we were saying that each of these assumptions, though it's kind of independent, we are kind of adding up these assumptions to all the structures that we will be dealing with. So we are saying that it will not only be elastic material, but it will also be a materially linear elastic material that we'll be dealing with. So the second thing which we talked about was material linearity, and therefore we were able to write this sigma ij as some set of constants which we call as EIJKL times gamma KL. Okay. So just to, there is actually a strict mathematical notation associated with this, that these are second order tensors and these are fourth order tensors, but it's beyond the scope of this course to introduce tensor notations. But nonetheless, I just want to give you a flavor of what we are doing over here, that these are essentially constants associated with any particular material, and so all of these are constants, and there are 3 into 3 associated with the stress and 3 into 3 associated with the corresponding strain, and therefore the total of 9 into 9 equal to 81 constants at this particular stage. Remember that before we made the material linearity assumption, we didn't even have an idea of any constants whatsoever, because those were nonlinear functions, and so they can be general functions, and they may not even involve certain constants. So it's a huge simplification going from a elastic material to a linearly elastic material. And again, here we have the same assumption that we had, though I said that we can have elastic, nonlinear, elastic, linear, linear, inelastic, linear, elastic, etc. What we would require from our course point of view is to add up these, and so now we are considering a state where we have a linearly elastic model, so which is what this holds for, right? And in all of these, there is the Einstein's summation convention that we will be using. So this essentially says that whenever the index is repeated, any of these indices are, remember, dummy indices. So when they are repeated, then there is an implied summation over their ranges. So in other words, K and L are repeated, but I and J are not repeated on the right hand side, which means that there is an implied summation over K and L over their entire ranges, and all I, J, K, L, all of these Latin indices, that is the English letters if you see. So these are the Latin indices. We will typically have a range 1 to 3. Okay. So whereas, so therefore the implied summation here is k equal to 1 to 3 and L is also equal to 1 to 3. And of course there are 9 such equations for each one of the sigma ij's, because still you have 9 stresses. So corresponding to the 9 stresses you would have 9 such equations, and each equation will have 9 terms that are associated with the 9 strains and the corresponding constants which are multiplying them. So this is what elastic linearly elastic material kind of leads us to at this point in time. So there are many more assumptions that we will make. The first thing that we already mentioned in the previous class was that there is no body moment, and we described it using a cuboidal element. Even more simply, we can use just a 2D element to showcase what we are trying to do. If let's say this is the x1 x2 plane, and then you're saying that when there's no body moment, essentially you're saying that these stresses that are acting on it, which are on the one face in the 2 direction, so it's tau 1 2 at tau 2 1, and similarly this is also tau 2 1, and this is tau 1 2. But remember that this is over a small element which is of size delta x1 along x1, and similarly about this direction you have a size of delta x2. Eventually you are going to take the limit as delta x1 and delta x2 tend to 0, right? So, but to start with, when you are having a non-zero delta x1 and delta x2, these are not equal to each other. So this is tau 2 1, this will be tau 2 1 plus the derivative of tau 2 1, which is a partial derivative with respect to x2, because your change is over x2. So dou x2 delta x2. Okay. So similarly, you start with a tau 1 2 on the left edge here. When you go to, by the time you go to the right edge, it will become tau 1 2 plus a small delta tau 1 2, which is going to be given by plus dou tau 1 2 with respect to x1, because the change is in x1 by an amount delta x1, so multiply that by delta x1, right? So this is the these are the shear stresses that are acting on these 4 edges that you see, and you typically try to take a moment about any one of these corners. The easiest corner to take the moment about is over this, because these are the more complicated expressions. If I take a moment about this corner over here, if I call these A, B, C, D, let's say. So if I take moments about C, you see there will be no contribution from these two, because they are passing through that point. The contribution will be only from this tau 2 1 and tau 1 2, right? Now tau 1 2, and we'll take a depth of this. This is delta x1 along x1, delta x2 along the y2 direction, and delta x3 in the direction into the whiteboard. So therefore, the surface on which this tau 1 2, for example, is acting is equal to the tau 1 2 stress is acting on an area, because we have to multiply the area to get to the force. So the force that is exerted by that is equal to the delta x2 times what is into the board, that is delta x3. So into delta x2 into delta x3 is going to give me the force. Now that force that is acting over here, when I want to moment about C, I have to take the perpendicular distance, and that perpendicular distance is delta x1. So the moment arm for this is delta x1. Okay, and now you check the direction in which this moment is acting. You see that this force is acting downwards, and I want to take moment about this point. So you can see that the moment is essentially like this, right? And x1, x2, x3 is actually coming out of the board. So the moment that you're going to have, right? So now this is a positive moment. On the other hand, if you look at tau 21, it is exerting a moment in the opposite direction, which is along the negative x3 direction. So you will have a negative sign associated with that, and that is a stress tau 21 and is acting on an area which is equal to delta x1 along the horizontal direction and a delta x3 into the board, right? So delta x1 delta x3. So that's the force. Now the moment arm for that, for the point C, is essentially your delta x2. So that is the moment arm for this, and of course we already taken the sign into account because this is unlike the first one, which was clockwise anti-clockwise moment. This is a clockwise moment which is taken as negative, right? So this is going to be multiplied by the moment arm, which is delta x2. Now essentially it's from your physics or even the statics course. This is essentially a free body diagram that we have drawn. So this is a free body diagram in a 2D space that we have shown it, but actually for a 3D element because we are taking into consideration the x3 direction as well, and we are essentially getting into a moment equilibrium, right? So this is an equation of moment equilibrium about k hat, which is the unit vector along the x3 direction, right? So now if these are the only two moments that I see here, but now I invoke this third assumption that I have over here, that I'm saying there's no body moment. So that's what you have there as well. The third assumption is no body moment. So when you have no body moment, it's very clear that there are no other forces or moments acting, because if there were body moments, that body moment will also have to be taken into account. So I will not only have these two terms, I will have a third term which takes care of that body moment per unit volume into delta x1, delta x2, delta x3, because that's the volume of this element. It's a cuboidal element, so it's just multiplying the length, breadth and height of this element. So you are going to get that, and then that's what the overall sum is going to be equal to 0. But now I don't have that because of no body moments, so I just have to set this equal to 0, right? So now if I set this equal to 0 and I can divide this whole thing by delta x1, delta x2, delta x3, which is the volume of that element. So even before I take the limit, it's very clear that from this, what falls out is that tau 12 is equal to tau 21, because it's the same delta x1, delta x2, delta x3, which is a factor on both the terms, and you can see that this is the fallout. And this is an example that we have shown in the x1, x2 plane. The same thing can be shown on the x2, x3 plane, and you would end up with a tau 23 equal to tau 32. And similarly, you can show that in the 3-1 plane, which we will show as tau 31 equal to tau 13. So using tau to kind of distinguish this particular shear stress as shear stress as opposed to a normal stress, which is sigma 11, sigma 22, sigma 33. But without loss of generality, we can always use sigma instead of tau here, and which is what we will do for most part of the course. We will, instead of tau, we will be calling this as sigma as well. But you will always know that when the indices are different from each other, it is a shear stress, and when they are same, it is essentially a normal stress. So we will use the notation sigma ij, and this becomes a normal stress when I equal to j. There are 3 such normal stresses, and similarly 3 such shear stresses for which I is not equal to j. Okay, and what this exercise has shown, all this, instead of writing it as three separate equations, I can write it as a single equation now, which says that sigma ij is equal to sigma ji, because anyway when I equal to j, sigma 11 equal to sigma 11 becomes a trivial thing. So it's whether I specify this is for shear stress or not doesn't matter. So it's always going to be valid, and therefore there are going to be only three non-trivial equations. So though there are 9 such equations, so essentially 3 of them will be repeating. Instead of left hand side equal to right hand side, it will become right hand side equal to left hand side. So 3 will go because of that. Other 3 will be associated with the normal stresses, so that will give you sigma 11 equal to sigma 11, etc. So all of them again are trivial. So what is non-trivial is of course this set of 3 equations, but always remember that it is under the condition that there are no body moments, and for this you actually don't need the first 2 assumptions. So whether this whether it is elastic or inelastic, whether it is materially linear or non-linear, doesn't matter. Just the fact that there are no body moments means that this is going to hold good. Okay. Now, just like we have done this exercise for stresses, we can do a similar exercise for the strains as well. And the strain, remember that your gamma ij is defined as 1/2 of dou u I by dou xj plus dou uj by dou xi. Okay, this is as far as the linear approximation is concerned. So there will be certain terms. If you have a non-linear strain, typically at least a quadratic term is very common. There are many different definitions of stresses and strains. It's not a unique definition, but once you have a particular stress definition, there will be a particular strain that is kind of compatible or conjugate to it. We will look at that when we introduce the next assumption, the 4th assumption. But right now, just be aware that there could be multiple definitions for strains and stresses, but this is one of the very common definitions. And here you can kind of cross verify with things that you are familiar with. For example, the normal strain gamma 11 is equal to dou u1 by dou x1. It's just the change in length along the x1 direction, and this is something that you have seen before as well, and that can be a direct fallout of this because I and j are both equal to 1 in this special case. So this becomes dou u1 by dou x1. The second term also becomes dou u1 by dou x1. So it becomes 2 of them, and there's a factor of half. The 2's cancel, and this is what you have left, right? So similarly, if you take an example of a shear strain, then you would have gamma 12 is equal to 1/2 of dou u1 by dou x2 plus dou u2 by dou x1, and by definition it's essentially the change in the right angle that happens. So because this is, remember, between any 2 edges is a right angle, and by the presence of these stresses, this is going to get elongated in this direction, going to get compressed in this direction, but essentially this angle is going to become larger than 90 degrees, this angle is going to become less than 90 degrees. So it's the change in the right angle that we are trying to measure over here, and typically this is this notation is called as the tensorial strain. So this gamma 12 is all these shear strains which are defined like this are defined as the tensorial shear strain, and there is something called the engineering shear strain, where you're taking this factor of 2 to the left hand side and calling it 2 gamma 12 is the sum of dou u1 by dou x2 plus dou u2 by dou x1, and that is what is that change in right angle. Okay, so this is actually half the change in the right angle. So the tensorial shear strain is half the change in the right angle, the twice of this, which is this is tensorial. So next is the engineering shear strain, is twice the tensorial shear strain and is defined as 2 gamma 1 2 is essentially the change in the right angle between x1 and x2. If it is any ij, it is the change in angle between xi and xj. So that's what we are talking about. So from an experimental point of view, it is typically this that you will be measuring, but for a lot of mathematics, when you're doing the derivations, it's much more convenient to use this, because once you use this, all of the second order tensor properties can directly be utilized for this, and therefore it becomes much more convenient in derivations to use this. But what is actually measured in your strain gauge by appropriate mounting of multiple strain gauges to get to gamma 1 2 is essentially twice gamma 1 2 rather than gamma 1 2 itself, and therefore that's the engineering shear strain as opposed to a tensorial shear strain, right? So this is kind of concludes the utility that we have got from these three that we have already stated, and in terms of this particular equation, how does it get simplified once we have these two. So let's start with the first thing that we did, where we showed that your sigma ij is equal to sigma ji. So this is what this whole thing boiled down to this, right? And from the very definition over here, if I interchange I and j in this particular expression for gamma ij, or for that matter 2 gamma ij, in either case, if I interchange I and j, you can see that all that is happening is the second term will come first and the first term will become second. So instead of something like a plus b, I'm going to have b plus a, and addition is commutative, so both are going to be the same. So essentially what this is, this definition, and this will be true when I introduce a quadratic term as well, you can verify. But since we are going to deal with another kind of linearity, already we dealt with one kind of linearity called material linearity. So the other linearity that we will deal with is essentially throughout this particular course, but it's not actually valid for most aerospace structures, is the fact that I'm going to set all of these higher order terms to 0, and that is what is called as geometric nonlinearity. So these are, linearity, geometric linearity, and in reality, this is not valid for most aerospace structures because the displacements or rotations are very large, and therefore you do need to take into account the quadratic terms, etc. over here. But even when you take the quadratic terms, your gamma ij will still remain equal to gamma ji, but I'm not showing you all that because it's kind of beyond the scope of this particular course. So what is important to notice, we have two conclusions that we have made. One is from the absence of body moments, gamma ij equal to gamma ji, and from the very definition of gamma ij itself, from the very basic definition, we have showed that gamma ij and gamma ji are equal to each other. So that's the second important conclusion from this. And they are coming from two different sources. This is coming from the fact that there are no body moments. This is coming from the fact that it is purely based on the definition of the strain itself. Okay. So now these are the two things that you kind of ought to remember. And how do you think that will simplify this equation that we already had from the first two assumptions? What is going to happen to this particular equation? How many equations did we have to start with? How many sigma ij's are there? Before we did all this, before the body moments, just up to this point, how many sigma ij's were there? Yeah? One? No, but remember that I and j are Latin indices taking on this range 1, 2, 3, right? So how many values can I take? 3 values. How many values can J take? 3. So how many combinations do you have? Yeah. So you had 3 into 3, 9 such equations, okay? And each of them had a number of terms on the right hand side. Like for example, if I take sigma 1, 1, it's going to have this going to be expanded based on Einstein's summation convention. What is Einstein's summation convention? Anything which is repeated, there is going to be an implied summation over that. Here K and L are repeated, therefore there is a summation over K equal to 1 to 3 and a summation over L equal to 1 to 3. So how many terms are going to be there because of that? Each of the stresses is going to have how many terms added to each other? It's going to be as many as there are gamma KLs, right? Because for each gamma KL, there's going to be one of these. So there's going to be a pair which is multiplying each other. Then again, if I change the rotate between KL, then I'm going to get more. So how many gamma KLs are there? Exactly. So same argument is valid. What Alexandra mentioned for stresses, Patrick has mentioned for the strains. So essentially you have 3 into 3, 9. So essentially you are having 9 terms in each equation and 9 such equations, okay? And that's why you have 9 into 9, 81 constants. That's what you had at this stage when you just made 2 assumptions, elastic and material linearity. Now you want to invoke 2 more useful things. One is purely from definition, so it's not even an assumption. So that's why I'm not even listing it out here. It is a pure fallout of the way in which we define strains, that gamma ij and gamma ji are equal to each other. But what is the fallout of the third assumption is that also the stresses are also behaving in a similar way like the strains, that they are symmetric, that sigma ij and sigma ji are the same. In other words, if I interchange those two coefficients or subscripts, it doesn't matter, you're going to get the same value, okay? Though where it acts is different, tau 1 2 acts on this phase, tau 2 1 acts on this phase, etc. But in terms of the values, the magnitude, both are going to be the same, sigma ij and sigma ji, right? Now what is that going to mean in terms of the number of equations that I have? So instead of 9 equations, is it possible that I can reduce the number of equations? Yeah, anybody? See, we had sigma 1 equation each for sigma 1 1 2 2 3 3. Those are the normal stresses, and we had 6 shear stresses: sigma 1 2, sigma 2 1, sigma 1 3, sigma 3 1, sigma 2 3, sigma 3 2, right? So now is there some simplification that I can have because of this? Yeah.
To just like 2 different like stresses?
Just 2? Which 2?
Like IJ and JI.
See, IJ and JI are kind of dummy indices. Reality is we are talking about this entire range. So right. So when I say sigma ij, I'm talking of 1 1 2 2 3 3 1 2 2 3 3 1 and the other 3 1 3, etc. So the total of 9 of them, right? But do I need 9 equations anymore once I have said this? So these are going to give me the 9 stress components, right? But how many stress components do I really need because of the new information that I have that these are equal to each other? Which means essentially that these 3 equations are valid, right?
So is it just maybe like 3 of those equations?
Yeah, there are 3 from the normal stresses, sigma 1 1 2 2 3 3, and these 6 equations that I had, I need only 3 of them, because if I have tau 1 2, I already know tau 2 1, I don't need another equation for it. If I already have tau 2 3, I don't need tau 3 2. If I have tau 3 1, I don't need tau 1 3, right? So I need only 3 equations for the shear stresses and 3 equations for the normal stresses, right? So I need only 6 equations. So instead of this 3 into 3 9 that we required earlier, we need only 6 totally, okay, which include 3 normal and 3 shear, okay. The normal ones are sigma 11, sigma 22 and sigma 33, and the shear ones are sigma 23, sigma 31 and sigma 12, okay. So if I have these 3, I can automatically get sigma 32, sigma 13 and sigma 21 as well, right, because they are equal to each other in the absence of body moments. Even if there were body moments and I knew how to calculate the body moments, I will still have a relationship between tau 12 and tau 21. In other words, if I know tau 12, I can calculate tau 21 as the difference based on the per unit volume or body moments that are there. So body moment per unit volume is what is going to make these two different from each other. So if I have an expression for that, like for example body force like gravitation, I know how to determine it. Just similarly for a magnetic material, I know the Maxwell's laws, etc., from which I can derive a relationship saying that this is going to be the body moment per unit volume. So I can always find that. So whether you have a body moment or not, the fact that you have an expression for body moment also means that I can make this reduction. But the special case of that is there is no body moment at all, and therefore I can just say that they are all equal to each other, right? So essentially instead of 9 equations, I have only 6 equations because 3 are repeating the same thing. It's not that there are no longer 9 equations, but 3 of those equations are just repeating whatever the other 3 of the others had already given you. So it's kind of repeated equations, so you just leave them out. So in other words, what you call as independent set of equations, right? Similarly, what happens to the right hand side? Remember that we concluded that each of these equations had 9 terms associated with the 9 gamma KLs, right? Because K and L were 3 having 3 values each, so 3 into 3 were 9, so you're going to have 9 terms. But now that you have from the very definition that gamma ij is equal to gamma ji, what are you going to make a conclusion in terms of the number of terms that are going to be there here? Would you still have 9 independent terms, or would they reduce? Exactly. So same argument holds, just that here we are talking of number of equations, here we are talking of number of terms in each equation, okay? That's the only difference that is going to be there, and therefore whatever is going to multiply gamma 12 and gamma 21 are going to be the same, and gamma 12 and gamma 21 itself are equal to each other, and I just make it 2 of those terms, right? So so out of these 9 terms, 3 are going to be multiplying normal strains, they remain as they are. As far as the 6 terms which are in terms of shear strains, those 6 terms on the right hand side, they are going to become just 3 terms, because a pair in amongst each is just giving the same information, they become double of each. So that's essentially what is going to happen. So in other words, you now have 6 equations for the 6 stresses in terms of the 6 strains. So essentially, how many constants will you have now? Now earlier we had 81 constants because we had 9 stresses and 9 strains to deal with. Now we have 6 stresses and 6 strains to deal with. So how many constants will you now have? 6 into 6, 36, right? So this 81 constants now becomes 6 into 6 equal to just 36 constants, right? So to start with, even after making the elastic assumption, we didn't even have any constants. They were very complicated nonlinear functions. Once we made material linearity, that became constants instead of complicated functions, so linear functions essentially, and those linear functions had 81 constants that we had to deal with. Now we have taken advantage of either the body moment is known or is 0, and the fact that the strains are all defined symmetrically, and therefore we have reduced it to 36 constants. Even if this body moment was unknown, then you would have 9 stresses to deal with and only 6 strains, and therefore you can do with 9 into 6, 54 constants, right? So it's just that this is the case with most materials used in aerospace engineering and many other engineering sectors as well, and therefore this is a valid assumption that sigma ij is equal to sigma ji, and in addition, from definition we have this, and therefore the end result after these three assumptions is that I deal with only 36 constants associated with 6 stresses and 6 strains, right? So not that there are no longer 9 stresses and 9 strains, just that the independent stresses are 6 at any given point in space and at a given point in time, and similarly the number of independent strain components are also 6, no longer 9, right? Clear? So now, instead of writing stress as typically the way it is supposed to be correctly written in any given coordinate system, is as a matrix like this, because once you have fixed a coordinate system associated with the element as well as the directions of the forces, then you have a 3 by 3 matrix. So then you had sigma 1 1, sigma 2 2 and sigma 3 3 as the principal diagonal elements, and these were all the normal stresses, and then you had the tau 1 2 or what we call as sigma 1 2. So that's sigma 1 2, sigma 1 3 and sigma 2 3, right? And the exercise that we have done with the no body moments is showing us that this is a symmetric matrix now, right? So you no longer have to deal with 9 independent terms. There are only 6 independent terms that you have to deal with over here, right? Now if there are only 6 terms over here, I might as well rewrite this sigma, though it's not a mathematically rigorous way of writing. I can write for simplicity this as just a column matrix consisting of 6 terms. So in other words, I can write the same thing as going in this order: sigma 1 1 2 2 3 3 and then 2 3 1 3 1 2. I have these 6 elements over here, starting with all the normal stresses and then going to the shear stresses. So instead of a 3 by 3 matrix representation, I have come to a column vector which is essentially 6 by 1, right? So this is the simplification, and the first 3 in this, remember, are normal stresses, while the last 3 are shear stresses, clearly visible from the fact that their subscripts are different from each other, right? So this is a transition that we have taken. This is mathematically rigorous way of putting it, and this is simpler way of putting it for our analysis purposes. And the same thing holds for your strains as well, that is your gamma ij, which was once again a symmetric matrix that you had over here if you're putting it in terms of engineering quantities instead of tensorial quantities, because anyway we are not going to use mathematically rigorous, which is essentially tensorial. So I might as well write the engineering way of putting it. So instead of having these as just gamma 1 to gamma 3 1 and gamma 2 3, these shear strains, I'm writing it as twice each, because then I can directly measure using my strain gauge what is the change in the right angle that is there, and that based on that I can just populate this. So that's the reason why this is much more convenient, because anyway I'm not going to use this anymore. I'm just going to use corresponding to that, I'm going to just put it as this way, right? So now I have a much more easier way of writing the expression. Remember that how I used to relate sigma and gamma. I was earlier writing sigma in a strict mathematical sense as sigma ij is equal to an E ij KL gamma KL, where there was an implied summation over K and L, right? Now instead of writing it in that way, I can just write it as sigma I equal to a Cij times a gamma j, okay? Or I can, to be consistent with that notation, I can put it this particular way, right? So where on the right hand side there is an implied summation over j, but now your Ij are not just 1 to 3 like other typical Latin indices, but here I and j take on values all the way from 1 to 6. They take 6 different values, 1, 2, 3, 4, 5 and 6, corresponding to these elements that you have in the 6 by 1 column matrix that we had introduced over here, both for the stresses and the strains, right? So now you can see that instead of a complicated 4-dimensional matrix that I needed to represent this E, to represent this C, I need only a 3 by 3 matrix that 6 by 6 matrix that I can put very similar to this on a plane of paper. I don't need a 3 or 4-dimensional matrix like what I needed over there, right? So here you are going to have a much simpler kind of a representation. So in other words, I'm going to equate this in equal to a matrix C, which is 6 by 6 matrix, and then I'm going to multiply that by this strain gamma. Is this clear? Yeah? Any doubts? Fine? So what I am saying is that this stress sigma now is equal to So you're going to have a 6 by 6 matrix that is going to multiply, and all of these are constants because of the fact that we already said it's elastic, it is linear, etc. That linear elastic material has made these constants, just that instead of 81 constants we now have 36 constants. But even though I have not written the lower half diagonal of this matrix, at this stage this is a fully populated matrix, and I have no way of saying that C12 is equal to C21 with the set of assumptions that we have already made up to this point. That is, these three assumptions are not going to help me decide on the relationship between C21 and C12. So I cannot write symmetric over here like I was writing for a stress matrix or a strain matrix earlier. I still don't have that luxury. Okay. So in other words, I have 36 independent constants at this stage. So I'm going to make a few more assumptions, some of which are valid assumptions, and then I'm going to get into the hazy areas of yellow, and then probably the danger areas of red slowly. Okay. But now, what is the next assumption that we're going to make in order to prove that this is a symmetric matrix, not a fully independent matrix? In other words, it can be fully populated, but if I know these 21 terms, because there are, remember, 6 into 6 are 36, 6 into 6 equals 36, of which 6 are diagonal, right? 6 of them are diagonal terms. So how many does that leave? 36 minus 6 are the off diagonal terms, right? Now 36 minus 6 is 30, but now in case I am able to prove that this is symmetric matrix, then I can say that this will also not be independent, only half of them will be independent, and therefore I will have 36 minus 6, 30 divided by 2, total of 15 off diagonal terms. Already I had 6 diagonal, so 6 plus 15, I will get a total of 21 independent coefficients or constants associated with the stiffness matrix. Is this clear? We had 6 by 6, which is 36, of which 6 are diagonal terms. So therefore, the number of off diagonal terms are 36 minus 6, which is 30. And if I am able to prove, this is still if, I have not yet proved that. With the next assumption, we will do that. But if I am able to do that, then very clearly I would see that these, once I get these 15, the other 15 would just be a mirror image of it, so we can just directly get it. So there are 36 non-zero coefficients, but of which only 21 are independent. Okay, so remember that. So what is that assumption which is required to make a conclusion that this matrix is also symmetric like sigma and gamma? So that assumption is the existence of what is abbreviated as SED, which is essentially your strain energy density. Okay, the strain energy density that is, as the name suggests, a density. In other words, it's measured as per unit volume, just like mass density is measured in kilogram per meter cube in SI units. It's a mass per unit volume. This is the amount of strain energy per unit volume. Now, like all energies, this has the unit SI units of joules. So a strain energy density has the unit of joules per meter cube. So what we are saying is that in the structural component, be it a spar, be it a skin, whatever, if I take an infinite similar element, which is a cuboidal element, it is going to contain certain energy which is stored in it. So what exactly is happening over here is that we are applying certain loads on the structure. When we are applying the loads on the structure, it is going to deform, and therefore that work that I did by applying the loads, and the point of the load has moved in the direction of the load application. So some work has been done by external loading sources onto the structure or structural component. So that work, it has not gone waste, it is stored within the structure, and when I release it, you know that the loading and unloading are the same curves like Nilesh pointed out last time. So what we are saying is that we are having that body which had stored the as strain energy, the work that I had done using external loads is now releasing that strain energy, and that release of strain energy can be used to do some work. So essentially we are talking of a conservative system. In other words, energy is conserved. You have applied loads, the point of application of the loads have moved by a certain distance, the product of them gives the work that has been done, If it's a moment times the rotation at that point of application in the direction of the moment, and that has done some work. All of these works get added up for all the elements within the body over a period of time, and all of that, as long as it's still within the elastic limit, is stored in that body. And once I release those loads, it's going to come back to its original shape, and that return to original shape can be used to do some useful works. In other words, whatever work I invested in it is going to come back as it is if it is a purely conservative system. Most systems, structures have damping, for example, what is called a structural damping, and therefore some dissipation is involved, and therefore not all of the strain energy might come out. And we saw when the material is not elastic but inelastic, the loading curve and the unloading curve can be different. Residual strain can result. So the area between these two curves gives you the energy that has been lost. It's like hysteresis, right? So when you lose that energy, so that's a dissipative system that you have, right? But nonetheless, in all of these cases, there is an existence of strain energy density. At least a part of the work that you do can be recovered even in such systems. But our focus is purely on materials and structures which are going to satisfy all of these conditions, all these four, and at least to this point we are going to have more, but we are going to have all of these, which means that we are dealing with elastic materials, and therefore all of the energy, the work that I have done has been invested as strain energy, as long as the system is not moving, in which case there can be part of it which is going in as kinetic energy as well, but right now purely as strain energy. When we want to deal with dynamics of structures, then we have to deal with both kinetic energy and the potential energy. This potential energy in this specific case is called as a strain energy. Not very different from your spring mass system, where you are having the spring extending or contracting with a linear spring constant, let us say. Then it is storing a certain amount of energy which is given by half kx squared, where x is the deflection of that spring, right, and k is the spring constant that you have. So same thing, you're going to have, instead of that k, that stiffness is going to be essentially this. And then you're going to have the deflections which are of different nature. Each one of them are associated with a particular kind of strain, some with normal strains, some with shear strains, but essentially just like half k x squared that you had, deflection squared, you're going to have a strain squared that is associated with that. That is what is a linear model, because linear is a linear relationship between stress and strain, but as far as strain energy is concerned, it will be quadratic. Just like in the spring constant, you know that for a spring you had, for a spring of you applied a force F, then this is K, this is spring constant. So this is going to have a kind of extension that is there, and that extension you can call it X or delta, and in terms of that you know that the force is equal to K times delta. That's why this is called a linear spring constant. The linear there refers to the fact that this particular equation is linear between the force and the displacement. But in the same problem, you know that the potential energy which is stored is not linear in delta but actually quadratic, because it's essentially plotting the force versus delta from 0, 0, it goes to that final value of F delta, and it's essentially the area under this triangle is the work that is done, and that entire work which is done is stored in this, because once again we are dealing with a conservative system. So this conservative system, you see, and of course it's a linear system as well. The linearity is between the force displacement, whereas the energy which is stored is essentially going to be your F times delta. So the area of this triangle is going to be U is equal to half F delta. In this expression, if you see, it seems like it is linear with F and delta, but F is also a function of delta, which you can substitute F is equal to K delta, and therefore you, using this equation into this equation, you end up with this particular equation that U is equal to 1/2 k delta squared. So in other words, the potential energy, or what you can also call as the strain energy in the spring, we don't see it from that point of view over there because we are dealing with single degree of freedom systems, and therefore we treat the spring as if it was a black box which is having certain extension. But if you look at each point in the spring, it's actually made out of certain material, and each of those material points are undergoing certain strain, and that stress and strain that they are undergoing is essentially what is resulting in the overall behavior of the spring in this particular manner. Now that's a very, very simple system. We are having much more complex systems which deform in multiple ways, not just extending in one particular direction by a delta, which is also there over here, contained within this, an extensional strain in 3 different directions, and then also 3 shear strains, and therefore we are essentially talking about an extension of this potential energy or strain energy expression. Here it was a scalar quantity k that was involved. Here we have a matrix k. In fact, it's a 4th order tensor, but we have simplified it and made it appear as if it's a 2nd order tensor with just 2 subscripts, but it's still not a 2nd order tensor. It is a 4th order tensor, but with these simplifications that we want to do just for mathematical notation on the board to be able to represent it, we are writing it in the form of a matrix. But nonetheless, at the end of the day, in terms of how it physically behaves, very, very similar to this K that we're talking about. And it's for no reason that this is also called stiffness, this is also called stiffness. It's just that a scalar quantity, here you have a 4th order tensor quantity quite innocuously being represented as a 2-dimensional matrix over here. Okay, so that's the existence of strain energy density. Still we have not answered why, if strain energy and strain energy density exist, will this matrix be symmetric? Okay, so that is still something that we have to yet to go to. We have only explained what is strain energy, what is the distribution of strain energy, and therefore the occurrence of a density associated with strain energy as joules per meter cube and energy per unit volume. We want to see, so what if it exists? How does it simplify this matrix for me? That is the question that we would like to address next. Any questions on this? Yeah. Yeah. So far we have not made any assumptions on the structure of the material. So that will be the 5th assumption. But even before we get to this, we want to now talk about the strain energy density. Okay. So now, just like for that simple spring, we said that it is 1/2 k delta squared. Here we are going to write that U, we will call it as U3D because it's 3-dimensional in the sense that it's per unit volume. Joules per meter cube is the SI units for this. Okay. Now that is just like a 1/2 k delta squared. You're still going to have that half over there. Instead of k, you're going to have this Cij system that you have over here, and then you're going to have this gamma ij, which is going to be squared associated with that, right? Now we are seeing that this is going to be associated with a particular strain, so, and that is going to be associated with a stress. But now you cannot have this in this particular form. There is something still wrong with this particular expression. So because essentially what is happening is that each term should be multiplied by the corresponding squared of this particular term that you have over there, right? So now what is actually happening over here cannot be explained properly. The reason is that we have kind of mixed up things. This is actually a 4th order tensor, but we are trying to put it in the form of a 2nd order tensor, and this is actually a 2nd order tensor being put as a 2nd order tensor. That's why the complication is arising over here, right? So in reality, let's go back to the notation that we used to have, which is the correct mathematically rigorous notation that we had, which is actually your Eij KL, and then you have your gamma KL, and this is squared. So now this is a right notation that we can have over here. So you are actually trying to extend over this. Now still again you have an issue, because once the summation over the KLs are going to be done, you are going to be left with Ij. There is no Ij on the left hand side. So still, even though we have gone to a rigorous E representation, a rigorous gamma representation, this is still an incorrect representation to have. So what is the correct way of doing it? So let's head to it and go to it in step by step. Okay, so what we have is an ability to go from the strain to the stress. So what is that? Essentially you are saying that your sigma ij is going to be a partial derivative of u with respect to gamma ij, okay, u3d. Okay, so this is now a little more clearer from a mathematical point of view. You can see there is a floating ij on the right hand side, a floating ij on the left hand side. There is no repeated index, and so this is quite clear. And it is also clear from the point of view of the spring damper system, where we had the F delta relationship using a K, and that can also be written in the same way, because there U is equal to half K delta squared. Now if I take a derivative with respect to delta, I get 2K delta divided by 2, the 2's cancel, and this becomes just K delta, and that is nothing but your force, which is essentially you're generalizing this to get to this. Okay, so this had resulted in F is equal to dou U by dou delta, which is equal to 2K delta divided by 2, which is equal to K delta, which is what we had started off with. Okay, so now you are essentially saying this particular thing, instead of a single spring constant, we are having a multiple set of spring constants. So that is essentially contained within this. Instead of a derivative of u with respect to delta, we are taking the u derivative with respect to gamma. So instead of a force, we are getting a stress. So that is the only difference that is happening over here. But essentially the simple equation or model that you had for the spring system, single degree of freedom system, is essentially what you are generalizing to a continuous system to get to this. Now what do you do? Now we already saw, because it's a linear elastic material, if I were to plot, as we saw in the previous class, if I wanted to plot any sigma ij with respect to a gamma kl, essentially because it's a linear elastic material up to the point that this theory is valid, so you're going to get a straight line which is going to be associated with that. And essentially what is going to happen is the strain energy density that we are talking about is nothing but not only the area of this particular curve, because this is for one ij with one particular kl, there are so many other ij's associated with each kl, and then you have all of that energy actually getting added up, which is why you have a summation over here. So in other words, we can write now your sigma ij is this, and this set of constants that we can have is now a derivative of sigma with respect to a gamma kl. So that gives you the eij kls. So let me write that expression explicitly. Okay, so Now you see this, your Eijkl is now going to be given by a second derivative of this, because the first derivative gave you the stress, and if you take the derivative of the stress with respect to the strain, you are supposed to get the coefficient, which is that what you are essentially getting over here, right? So second derivative of the strain energy density with respect to the strains is going to give me my Eijkl, right? Now from the fact that the stresses are symmetric, we have already shown that I and J, if I interchange, it doesn't matter. From the definition of strain, I have shown that the strain is symmetric, and therefore if I interchange K and L, I do not have any issue, it will remain the same, right? So KL interchange is coming from the strain symmetry, and Ij interchange without any overall change is coming from the fact that no body moment and therefore a stress symmetry, right? Now what we have done so far are both called as minor symmetries, because they are both with the superscript or both with the subscript, right? So these are called as minor symmetries. This is also a minor symmetry. Okay. Now we are in a position to have a conclusion over a major symmetry. In other words, if I interchange Ij, take this subscript and put it as a superscript, and bring the superscript KL as a subscript, in other words, I have E instead of Ij KL, I have E Ij KL. Okay, is this true? This is the question that we are trying to ask. This came purely from stress, the one came purely from the strain, but now from the fact that we have this definition for Eijkl, can I showcase that these two are equal to each other? In other words, if I bring KL down and take Ij on top, is it going to remain the same? Which in turn means that this matrix is symmetric, because that is how this was essentially populated from the Eijkls by making it a much more compact notation. Okay, so it's just a pure compact notation that we are having here. So to prove Cij matrix is symmetric, all that I need to do is, at the more rigorous mathematical level, I have to prove these two tensors are equal to each other. In other words, this particular tensor is having not only minor symmetries but also a major symmetry. So this is what we call as a major symmetry. Why major? Because you are essentially exchanging pairs of indices rather than individual indices. Here you are exchanging individual indices and saying it doesn't make a difference. Here I am interchanging a set of indices with another set, so it's a major symmetry that we have to get to. So still the question mark remains, is this equal? If this is equal, then yes, this will be symmetric and your Cij will be equal to Cji. So I have a huge advantage that instead of 36 constants, I will be dealing with only 21 constants, 6 diagonal and 15 off diagonal. The other 15 I can get from these 15 because they are equal to each other. Okay. So now, is it true? Let's get to this. Now you see that what we have shown here is that your EKL Ij is given as dou squared U3D by dou gamma Ij dou gamma KL. In other words, the right hand side is a second derivative. It's a second partial derivative with respect to two quantities. First with respect to gamma KL, then with respect to gamma Ij. Now a very interesting and useful fallout of calculus, differential calculus, is that when you're taking a second derivative with respect to two different quantities, it really doesn't matter with respect to which variable you take the derivative first and with respect to which variable you take the derivative next. So in other words, I can write this either as dou by dou gamma Ij of dou by dou gamma k L u. That is one way of writing this. Alternatively, I can interchange these two and take the derivative with respect to gamma ij first, and then with respect to gamma kl, I would end up with the same thing, and which is nothing but your dou squared u3d by dou gamma kl dou gamma ij, right? So now I've just, all that I've done is interchange these two, and therefore what I am getting up here is that this is equal to E KL as subscript and IJ as superscript, which is essentially reverse of what I started off with. Okay, so this is the major symmetry coming purely as a fallout of an property of differential calculus, that a second derivative, or for that matter any multiple derivatives you want to take of a function with respect to various variables, the order in which you take the derivatives doesn't matter. You can take whichever is more convenient to you first and then keep on going like that. Okay, so whichever you're taking derivative with respect to, you are essentially keeping all others the same. You're just taking derivative with respect to that, and then you're going marching in steps in order to do that. So the order of marching doesn't matter, which is from which we are able to show that there is not only minor symmetries followed from strain definition and from the stress symmetry because of the no body moments, but also because of the very definition from differential calculus we can show. Of course, it's all under the first two assumptions. It's that it's an accumulated assumption. Now it's not an independent assumption that we are making over here. The existence of SED leading to Cij symmetry is in the presence of a linear elastic material, because only for linear elastic material this expression is valid first of all. Then I can interchange and play around with it and show that it is equal to Eijkl, that is interchanging of the superscripts and the subscripts, and therefore in other words, if a particular stress component Ij component causes a particular strain component Kl, this stress component KL will cause a strain component Ij, and their relationships will be similar to each other. So this is what is known as the law of reciprocity. So in other words, there's a reciprocal behavior, and which is again in the simplest form is your Newton's third law. Every action is equal to equal and opposite. A reaction is met by it, right? So essentially what you're saying is that if you're having a certain load or stress that is applied here, and you're measuring a strain, a particular strain component because of that, instead of that strain component you apply its conjugate stress and you measure the strain in the original stress direction. So then you are essentially saying that these two are related in the same way. That is the physical meaning of what we are talking about, and therefore you no longer need the question marks over here. So you remove the question mark that yes, these two are equal to each other, and because these two are equal to each other, your Cij is equal to Cji, because that's just a compact way of representing the same Eijkl, and therefore this matrix is symmetric, and in turn therefore you have only 21 independent constants to deal with. In other words, if you are going to do an experiment, we thought we had to do at least 81 experiments to determine all the terms. Then we said that no, 36 experiments were enough after making an additional assumption. Now we are saying that no, 21 experiments are enough for me to determine all of these coefficients, right? Now we will see there are further simplifications that can be made based on the structure of the material. What is the material's constituent, how it is kind of structured within, we will be able to make certain approximations based on that. Is this clear, or do you have any questions or doubts on this? What is the name of the C matrix?
Yes.
Yeah, it's a stiffness matrix.
It's
Yeah, yeah. It's just this is also stiffness, the tensorial stiffness. This is a matrix representation of the stiffness. Okay, so essentially, as I said, this is not mathematically rigorous, but this is the way in which you'll see all of the literature and all textbooks will typically represent, because it's convenient. Because why is it not mathematically rigorous? Because I'm putting the stress as a column matrix, though it is a second order tensor, and the appropriate representation for that once the coordinate systems are chosen is pair of coordinate systems are chosen is a square matrix. Instead I'm having a column matrix. Similarly, same thing holds for the strain, and because of that simplicity I'm getting a simplicity in the representation of a 4-dimensional matrix instead as a 2-dimensional matrix, and therefore both are stiffnesses, just that how you're putting them together in a compact way is the advantage. Yeah, so now any other questions on this? Okay, so let me just clear the board a bit. So the next assumption that we are going to make, as I said, is going to be in terms of the material's structure. So far we have not said anything about the structure of the material itself. Is there some symmetry associated with the structure? So all the things that we have talked about are symmetries in the stress, symmetry in the strain, symmetry in terms of the mathematics because of the way the differentiation can be interchanged, and therefore a major symmetry in the stiffness, right? So symmetry in the strain, stiffness, and the stress is already covered. Now we want to see, is there a material symmetry? In other words, is there a plane of symmetry in the structure? So in other words, if I take a cuboidal element like this, then I draw the mid plane of this. I want to see, is there a way in which the properties are reflected on either side. In other words, at a certain distance from the mid plane, if I go, I have a certain property. If I go below, will I have the same property? Okay. Similarly, can I have another plane of symmetry like this, another plane of symmetry like this? If I have all those 3 planes of symmetry, then I call this material as orthotropic. And all composites, fiber reinforced composites, long fiber reinforced composites, which are continuous, having continuous fibers, are all orthotropic materials in the principal material directions. By which we mean, one of the coordinates has to be parallel to the fiber direction, the others have to be perpendicular to the fiber direction. They can be in any way, but mutually perpendicular to each other, essentially a dextral triad that we are coming up with. Now, when you have such a system of coordinates introduced, then I have 3 planes of symmetry associated with each of them. If I call that coordinate system as x1, x2, x3, then x1, x2 becomes one plane of symmetry, x2, x3 becomes one plane of symmetry, and x1, x2 becomes another plane of symmetry, and I can take advantage of that. Once these planes of symmetry are there, I can use either mathematics whereby I have a so-called rotational transformation. So I use a matrix, let's say, called R, which is almost like the identity matrix, except that this last term, which in an identity matrix should be 1, I am instead, let's say, putting it as, this last term, which should also be 1, I am instead putting it as -1. What does it mean? If I multiply any property and I still get the same property, essentially it means that about the x3 axis there's a plane of symmetry. In other words, your x1, x2 is a plane of symmetry. So this, if a multiplication of this with the appropriate tensor quantities by multiple times, because if you have a stress, you have to do this multiplication before and after by R transpose and R. On the other hand, if you have a quadruple rank or order that is there for the stiffness matrix, you have to multiply it once again by this. Essentially you are coming up with this. So under the matrix being here, you get back the same matrix. So then you are saying that there is a plane of symmetry. So it's very easy matrix. You can see, you can easily multiply this with that, and you can showcase that in this particular case you are having C12, C13, C23, and the rest of these have to be all zeros. If they are not zeros, what will happen? This equality will not be valid. So this equality is what is giving rise to these zeros. In other words, I was worried I had to do 21 experiments. Now you see how many experiments do I have to do? I said 21 because I had 6 diagonal elements, 15 off diagonal elements, 6 plus 15 was 21. Now I still have those 6 diagonal elements. How many off diagonal elements do I have to determine? Yeah, only 3 are left, right? The rest are all known, zeros, right? So I have only 3 more to determine. So how many totally? 6 plus 3, 9, right? So I need to do only 9 experiments now because of the next assumption that I am making, which is orthotropy. Okay, so this is the assumption that we are saying that, and from the name itself you can make it. The prefix is ortho, which is the same in orthogonal, for example. It's essentially talking about right angles or a rectangular or a dextral triad or things which are perpendicular to each other, right? And tropy means tropical, essentially means direction. Okay, so there is some kind of a symmetry associated with the directions along 3 mutually perpendicular directions orthogonal to each other, and which is why we call it orthotropy. There's another tropy that you would have heard of, isotropy, an isotropic material, which is essentially saying that it's the same in all directions. Doesn't matter which direction I turn, the property is going to be the same at a given point. So that is, or a given point in space and time. So essentially I'm saying that that is isotropy. That is the simplest case that you can have. Anisotropy is any arbitrary direction. You could have entirely different properties. That's the most complicated case you can have. And now orthotropy is a situation where you have 3 planes of symmetry, and therefore if I reflect either about the x1 x2 plane or x2 x3 plane or the x3 x1 plane, I am always going to land up with the same properties, which means that it is not possible for these couplings to happen, because remember, all of these, whichever off diagonal term is there, including these, are essentially a coupling between 2 different kinds of stresses and strains. In other words, it's not if a sigma 11 is causing gamma 11, sigma 23 is causing gamma 23, etc. Those are all on the diagonal. Those are all diagonal representations here. It's only when a sigma 11 causing a gamma 23 or a sigma 31 causing a gamma 22, etc., different stress and strain correlation, that is what is going to go into the off diagonal system. Okay. Now, the fact that these are going to be equal to 0, one, you can prove using this transformation, that is pre and post multiplication by this rotational transformation. This is of course for just the x1 x2 plane. Similarly, if I want to do it for the x2 x3 plane, I would put this as positive 1 and this would become minus 1, right? So the same exercise will have to be done for so this is R1. Similarly, you would have R2 equal to 1 minus 1 1 0 0 0, and then again for R3, which is for the plane of symmetry associated with the x2 x3 plane. So you would have to do this once you do all of those, that's when you get all these as zeros. Okay, so that's a mathematical way of getting to it. There's also a physical way where you can say that you can start with now if x1 x2 were a plane of symmetry, what this is essentially saying is that if for example I apply, let's say sigma 22, that's the only stress that I apply, and then I monitor one of the let's say the shear strains, so then on this phase, which is essentially your x2 x3 phase, you have an element like this on the top. At an equal distance, you have an element like this. If suppose this resulted in a gamma 2, 3, right? So what am I talking about over here? A relation between sigma 2, 2 and gamma 2, 3, right? Sigma 2, 2 means I have to look at the second row. Then I have to look at gamma 2, 3 means I have to look at 1, 2, 3, fourth column, okay? So it's the second row, fourth column, 1, 2, 3, 4. So essentially I'm talking about C24. So it is this element which I want to check. Now if that were non-zero, then these two cannot deform in the same way. They cannot shear in the same way. If they have to shear in the same way, that shear has to be equal to 0, then only they can be equal to each other. We can physically argue that out. So instead of having to do it mathematically like this, you can make physical arguments for each one of these to say which strain and which stress is it relating, and therefore which symmetry are we talking about, and therefore for that symmetry to be present, the only possibility is that those are going to be 0. So that is the reason why C24 is 0. Similarly, you can argue out other terms that we have set to 0 as well. So all of these are zeros. Right? Now these somehow escaped. These three off-diagonal terms, apart from the diagonals which cannot be 0, because once the diagonals are 0, we get a situation where the strain energy is not positive definite. Okay? In other words, you're going to have a strain energy which can be negative as well in certain situations, which is not physically feasible or possible, and therefore one of the necessary conditions for this to be positive definite is that all elements here in the diagonal have to be positive, the principal diagonal, right? But there are other conditions that alone is not sufficient. It's a necessary condition but not sufficient. Let's leave that alone because that's not important or relevant for us right now. But what is important is I'm asking you, how come these guys escaped? What do they actually mean? Your C12, C13 and C23. There is some kind of commonality in terms of what is the effect that they are having. Let's take C12 for example. Which are the two quantities it is relating? Look at this stress, look at this strain. Which row is it in? Which column is it in? C12, which row is it in? Which row of this matrix is C12 in? Row. Yeah, first row, right? So it's in the first row. So it's essentially talking about sigma 11, okay? So that's the stress that I'm talking about. Which column is it in? Second, huh? So it's relating the second quantity. So in other words, it's a relationship between sigma 11 and gamma 22. But remember, we have already shown that this is symmetric. Is there one more place where C12 will be there? Why is it symmetric? Because there is existence of strain energy density, okay? If it is symmetric, will C12 appear one more time in this matrix? Where? If so, where? Yeah. Yeah. So instead of C21, we are going to have a C12 as well, okay? Because C21 and C12 are equal to each other, okay? So it's not only relating sigma 11 to gamma 22, it is also relating what? Yeah, sigma 22 to gamma 11, right? So it's relating sigma 11 to gamma 22 and sigma 22 to gamma 11. It's the same quantity which is relating both, okay? So what is it physically? So in other words, I'm applying a normal stress sigma 11 and I'm getting a strain gamma 22. So normal stress, normal strain. So what? You're already familiar with this effect. We in fact talked about it a little in the previous class also. What is this called? Young's modulus is the direct relationship. That's like your Hooke's law. So essentially a sigma 11 causing a gamma 11, or a sigma 22 causing a gamma 22, or a sigma 33 causing a gamma 33. So essentially it is these three elements in the diagonal which are essentially coming out of a Young's modulus like behavior. Of course they have other terms as well, but predominantly that is the main effect which is going into your C11, C22 and C33, right? But C12 is not Young's modulus. What kind of an effect is that? Because you are trying to pull it in one direction and it is having a normal strain in another direction. What is that effect called? Yeah, Poisson's effect. So we talked about Poisson's ratio last time. It can have for isotropic materials a range from -1 to +12. In the case of composites, up to the assumptions that you have made, it can have beyond -1 and beyond +12 also, and it has different in different directions. So we can showcase that as well. But what is more important is that the reason why these are still surviving is that they are essentially Poisson's effects, and Poisson's effects will not affect this symmetry, plane of symmetry that we are talking about. It doesn't matter because I am applying a sigma 11. So in this case, let's say relationship between sigma 22 and sigma 33, right? So I am trying to pull this plate in the 2 direction. It is having a contraction in the 3 direction. Similarly, if I pull in the 3 direction, it's having a contraction in the 2 direction, and both can be same without violating the plane of symmetry. So that is why, in spite of this being a plane of symmetry, you can still have a non-zero and still the reflection will still work. So as far as these 3 terms are concerned, and what is so special about them that they survive is the fact that all of them are coupling only normal stresses to normal strains. Okay, they are not involving shear stresses coupled with shear strain, or shear stresses coupled with normal strain, etc. Okay, what has disappeared is entire set of coupling between normal and shear, or shear and normal, and also between shear and shear. So you see, there's even shear and shear cannot survive once you introduce planes of symmetry, because that's what reality is for most composite materials, and there you are having planes of symmetry because of the geometry in which we are having them, that is the fiber geometry, continuous long fibers, and therefore if you are introducing a coordinate system which is a principal material coordinate system, one axis is parallel to the fibers, 2 and 3 axes are perpendicular to the fiber, which are called as the transverse directions, then we will see that there are 3 planes of symmetry, x1, x2, x2, x3 and x3, x1, and they will make all the normal and versus shear couplings disappear, which is a 3 by 3 matrix over here, and then this off diagonal matrix, which is 3 elements over here, which is just coupling one direction shear with another direction shear, that is a sigma 2,3 with a gamma 3,1 or a sigma 2,3 with a gamma 1,2. Those can also not exist because they will violate the plane of symmetry. Okay, so this is the reason why you will see that it's only those 9 plus 3, 12 coefficients which have gone, and once 12 have gone out of your 21, you are left with essentially 9. 21 minus 12 being 9, of which 6 are diagonal terms and 3 are off diagonal terms. And out of those diagonal terms, again you have a variety. The first 3 are essentially associated with the normal couplings, not couplings but normal relationships and direct relationships, and this is the shear direct relationships. Okay, so these are all, just like Aryek pointed out, these 3 are essentially like a Young's modulus kind of effect. These 3 are what modulus kind of an effect, 4, 4, 5, 5 and 6, 6. If these 3 are Young's modulus effects, as you said, these 3 are Poisson's effects, as Babu pointed out. What effect are we talking about over here, any of you? What is the coupling? Let's take C44 for example. It is in the 4th row, 4th column. Okay, 4th is 1, 2, 3, 4, which is it, sigma 2, 3. Same way here, 4, 1, 2, 3, 4, it's 2 gamma 2, 3. It's a direct relationship between shear stress in the 2, 3 plane with the shear strain in the 2, 3 plane. What relates shear stress to shear strain? Which modulus? Shear modulus, right? So essentially you can think of these as these 9 quantities as one which is dependent essentially on the Young's modulus, one which is essentially dependent on the Poisson's ratio. Not that other quantities will not come into defining them, but in terms of an effect. This is a Poisson's effect, this is a direct normal effect, and this is a direct shear effect that is coming over here. Okay, so 3 different types, and this is valid if and only if you are putting your coordinate system such that one of the coordinates is aligned with the fiber direction, the other 2 are aligned in directions which are perpendicular to the fiber, obviously, right? So, and mutually perpendicular also. So only under such a situation this simplicity will arise. If you put for the same composite material coordinates which are rotated from this some other direction, x1, x2, x3, you can end up with a fully populated matrix. But that fully populated matrix will still have only 9 independent coefficients. Those 9 independent coefficients along with that rotation angles that you have theta 1, theta 2, theta 3 will make this fully populated, but in terms of C11, C22, C33, C44, C55, C66, C12, C13, C23, theta 1, theta 2, theta 3, in terms of those 12 quantities, I can find functions which will represent every term of this particular matrix. It will still be symmetric. So in other words, there will be only 21 which are independent, but those 21 also you will see that only 9 are really independent, because once theta 1, theta 2, theta 3 factors are put in, you can get the others as well. But this is the simplest way in which you can represent a composite material in the principal material directions. And principal directions you're probably aware of. You talked about principal moments of inertia, principal stresses, principal strains, etc. Right? So those are all for second order tensors, but now what we're talking about principal material directions which are associated with the fourth order tensor. Okay, slightly more complex, but the concept remains the same, because we have very innocuously reduced that fourth dimension representation, 4-dimension representation as just a 2-dimensional representation, a matrix, and that's why you're seeing a lot of fallouts into this in terms of what you already know. Okay, so that's as far as the fifth assumption of orthotropy is concerned. We have 9 items to be determined, which means 9 sets of experiments to be done. Now let's see, can we do something more? Can we simplify it even further? One of the simplicities that you can see is right here in terms of a single layer. If you take, let's take the top layer for example, all the fibers in that are parallel to the width of this. So this is the length, this is the width, and this is the height, and this is along the length. So along the breadth. So if you see, all of these fibers are along the breadth of this top layer, right? If you take the bottom layer for example, they are all parallel to the length. Okay, and these are at different angles to both the length as well as the width. But any layer that you take, there are some things which are called as structural coordinates, which are aligned with the length, width and height of this laminate, which I will call as x1, x2, and x1, x2, then x3 goes up. Okay, so in addition, I can have an x1 prime, x2 prime, x3 prime, which are associated for each layer along the fiber direction I call as x1, and perpendicular to the fiber direction, one this way, one that way, I will call as x2 and x3. Okay, but that will be different in different layers because the angles are different in different layers, right? Now that is a principal material direction, whereas the overall thing that I was talking along length, breadth and height is a structural directions, and in general they will be different from each other. For the bottommost layer as shown in this picture, this is an example. So bottommost layer here, you would see that both will coincide, the structural and the principal material directions will coincide, because the fiber direction is along x1, which is along the length of the structure, and the other two which is along the width and the thickness are both perpendicular to the fiber direction. Okay, and here is very simple transformation will give that, because this is the x1 direction as far as the material is concerned, but this is the x1 as far as the structure is concerned. So just a 90-degree transformation will be good enough to deal with. Now for the sixth assumption that we are going to make, we are going to go beyond orthotropy. What we are going to say is that if I take let's say the top layer, then I have certain properties which are very distinct along the fiber direction. But if I take perpendicular to the fiber direction, that is, this is x2, right? So along x2 I have certain properties, but if I take either x1 or x3, I'm only looking at the top layer, remember, both are perpendicular to the fiber, because this is perpendicular in this way, this is perpendicular in this way. So essentially both are going to have the same properties. Okay, so in addition to all the simplifications we have made with those 5 assumptions and resulted in this simple matrix that we have now one more thing which is coming purely by just visually looking at this, and similarly for the last layer as well, and even for these layers, if I put it along that principal material directions, I can always say perpendicular to the fiber, whichever direction I take, the properties has to be the same, which is what is called as transverse isotropy. So in other words, isotropy, you know, properties are the same in all directions at a given point in space and time. Now we are talking of not full isotropy, but transverse isotropy. Transverse always means perpendicular to the fiber. So in a plane which is perpendicular to the fiber, all directions are one and the same. In other words, every direction in the plane, which, if this is a fiber, let us say, this is a plane which is perpendicular to the fiber, I take this direction, this direction, this direction, doesn't matter. All those directions are one and the same as far as material properties of that layer is concerned, and it's all going to have transverse properties. So that is essentially what you're saying by transverse isotropy, and when you do that, you will see that further simplifications arise. Now let's for simplicity take the bottommost layer over here, because that is identical whether it's the structural axis or the principal material directions, because x1 coincides with that, right? So now which is the plane of symmetry there? x2, x3, because x1 is along the fiber direction, x2, x3 is the plane as far as the last layer is concerned, which is a transverse plane, and there has to be isotropy in that. What does isotropy mean? Just that the properties, irrespective of whether it is x2 or x3, should be the same, right? Which are the properties which are only dependent on x2 and x3 is what we will look at. Okay, so now very clearly what it is saying is that if I interchange 2 and 3, I should not have any difference. In other words, this is having 1 as its first subscript. I'm only interchanging the next 2, which is associated with 2 and 3, because it is associated with sigma 1 1, sigma 2 2 on this side, and gamma 1 1, gamma 2 2 on this side. So in other words, these two quantities should be equal to each other. Okay, because what is it saying? This is relating sigma 1 1 with gamma 2 2, and this one is relating sigma 1 1 with gamma 3 3. Now both gamma 2 2 and gamma 3 3 are perpendicular to the fiber. Remember, this is fiber direction 1, perpendicular to the fiber is x2 and x3. So now x2 and x3, I'm applying a stress sigma 1 1. I'm seeing what is happening to my gamma 2 2 and gamma 3 3, right? Both should behave exactly same way, right? It should, if it's compressing by a certain amount this way, it should compress by a certain amount this way. In fact, any direction I take, it should compress by the same amount, because all directions there in that plane, perpendicular plane, transverse plane, are one and the same. So which essentially means that your C12 and C13 should be equal to each other. Similarly, if you take these two quantities, sigma C22 and C33, they should be equal to each other, because what does C22 do? It relates sigma 22 to gamma 22, and what does C33 do? It relates sigma 33 to gamma 33. Now both are essentially in the transverse plane. In other words, I'm trying to pull it in this way, how much is it going to get extended by? If I'm going to pull it in this way, how much is it going to extend it by? In fact, if I pull it in any direction along that plane, I'm going to get the same effect. So in other words, in that plane, within that plane, if I'm going to apply any tension stress, then I'm going to get an elongation strain which is going to be of the same value. So in other words, your C22 and C33 are equal to each other. I got one equation here, I got another equation here. Let's go forward. Now we look at these two, C55 and C66. What does C55 relate? it relates sigma 31 to gamma 31. Similarly, your C66 is relating a sigma 12 to a gamma 12. Okay. Now, if you look at whether it is 31 or 12, it is having one direction which is along the fiber and another direction either 2 or 3, both of which are perpendicular to the fiber. I can interchange 2 and 3, doesn't matter, it's going to be the same. So same way here also, the two stresses that I am talking about are sigma 31, sigma 12. One of the directions is 1, which is fiber direction, the other direction is perpendicular to the fiber. I don't care whether it is 2 or 3, in either case it is perpendicular to the fiber. So it's very clear that these two quantities are also equal to each other. It looks kind of different because you're talking of 5s and 6s over here, but remember that all of these were followed from EIJKL, which all had 1, 2, 3s only. And there, if you actually look at what C55 is or C66 is in terms of EIJKLs, then you will very clearly visualize all that you're doing is interchanging 2s and 3s, and you will get the same quantity. Therefore, these two are equal to each other. Because of the fact it's artificial 6 dimensions that we have introduced here, all the way to subscript 6 rather than only up to 3, and which is why this might seem like a little convoluted to you, but if you look at from what you are trying to replace, then you will see it's very clear, because one is relating sigma 31 to gamma 31, which is essentially stresses and strains which are involved, which are shear and shear in the LT plane. That is, one is longitudinal direction, which is 1, and the other is transverse direction 3. Now again, if you go to the last 6 term, it's relating sigma 12 to gamma 12, which is also LT, In other words, I'm replacing all the 1s by L, longitudinal direction, fiber direction, and all the 2s and 3s by T, which is the transverse direction. So you can see that these two are one and the same, right? And of course, the order doesn't matter. So because we already showed that this is symmetric by very definition, so it doesn't matter. So don't be bothered about that, right? So now that is as far as transverse isotropy is concerned. So I think we'll probably stop with this. We have just a few more assumptions, most of which are kind of hazy assumptions, which we're not very comfortable with, but most people make it. So we will visit that and see what are the advantages of it, whether we need to make it, or if we make it, what are the utilities, and if we don't make it, how can we go about it, which is what is more realistically or practically useful. Thank you.